All right, so now we're moving on to the momentum section. And the motivation for needing momentum as opposed to needing work and energy is that sometimes energy is not conserved because there are other forms of energy that it might happen. So in a collision specifically, we might lose energy due to physical deformation when things collide or things explode, when we're converting chemical energy into other forms of energy. Remember, work and energy only handles the mechanical forms of energy, but there are other forms of energy that exist. And so that's why we had to introduce the idea of linear momentum, was that it could not, work and energy could not handle all those possible scenarios. So momentum is a vector quantity. It's mass times the velocity, so it points in the same direction as the velocity vector. Okay, so it is a vector quantity. Unlike work and energy, we didn't have to worry about the directions in terms of like x component of work or x component of energy or anything like that. We only had a scalar quantity, but for linear momentum, we do have to consider the vector nature of it. Okay, momentum is vector quantity. Impulse is that this is our key equation. Kind of like in work and energy, we use work was the change in energy. Here we're going to do the impulse is the change in the momentum. This is our key equation. Now, just keep in mind that even though the process is going to be very similar to work and energy, because of the vector component nature of this, it is going to matter. Okay, so an impulse is required to cause a change in the momentum of an object. That's the core principle. It's just a rearrangement of Newton's second law. Okay. So it's nothing like super fancy, but it's just a way we interpret and understand Newton's second law that allows us to use the impulse momentum. And similarly, if you have an area under a force versus time graph, that's going to give you the impulse. So the other part that is actually thrown into Unit 2 now, but used to be that I incorporate more into Unit 4. It's technically a Unit 2 topic according to College Board, but I still include it in with the linear momentum, is center of mass. Center of mass equation is about this. Where is the location of the center of mass if you have multiple objects in a system? So then what happens is if you can combine multiple objects into a system, which we often do for the purposes of collision, we may want to know what is the center of mass of the object and the velocity of the center of the mass. And it is the sum of the mass times its position divided by the total mass, or it is a sum of m times v, which you can see here is a sum of their momentums divided by the total mass here. So the center of mass can be calculated by taking a weighted sum of the position of the objects, and the velocity of the center mass can be calculated in a similar way. Now, the huge advantage of this is that a lot of times, if you incorporate a system correctly, and there's no impulse on the system, right? Very common, where this part might be zero, then therefore the change in momentum is zero, and that's what we call conservation of momentum. So when is momentum conserved? Is when there is no external impulse acting on the system. Now, what is the system depends. A lot of times in a collision, we will include both objects in the system. But one thing to keep in mind is if the momentum of the system doesn't change, the velocity of the center mass doesn't change, because the momentum of a system is going to equal the total mass of the system times the velocity of the center of mass of the system. Okay, so that's one thing to keep in mind. Like this quantity, when you have this velocity center of mass, which is the sum of all the individual momentums divided by the total mass here, right? This part you can read as the total mass. You just move that up over here. M total times the velocity of center mass is just the sum of the momentums of all the objects in the system. So this is the momentum of the system here. It's just the total mass times the velocity of the center of mass. Okay, so that's the big idea of conservation of momentum. If there's no external impulse, there's no change in momentum. In a collision, if both objects are part of the system, there's no external impulse, and so then we do conservation of momentum. We'll go through the problem-solving steps, but basically, you calculate the total momentum before collision, after collision, and then if there's no external impulse, then we say the momentum is conserved. You set them equal to each other. Elastic versus inelastic collisions. This is a very, very confusing topic for most people. Elastic collisions are where the total kinetic energy system stays constant. It has nothing to do with bouncing or anything like that. Elastic collisions tend to bounce. They will bounce during the collision, but just because it bounces does not mean it is an elastic collision. When you are asked to justify whether it's an elastic or inelastic collision, the justification is whether the kinetic energy is conserved before and after the collision or not. Inelastic collisions, it's not that they stick together, okay? Yes, when they stick together, those are inelastic collisions, but that doesn't mean inelastic collision always has to be sticking together. As long as the total kinetic energy of the system changes, then it was an inelastic collision. Okay? So keep in mind that because momentum is a vector quantity, it may be conserved in one direction, but not in another direction, depending on the nature of the forces. So you got to keep that in mind. It is a vector quantity. We have to assign positive directions and do it just like we did with vectors, which I know is a big adjustment since we spend so much time and work and energy not doing that. So if we look at the problem-solving steps for linear momentum, it's going to look very, very close to the work and energy. Ultimately, at the core of this is you're doing impulses that change in momentum. We want to identify the system. When including both objects that are interacting, either pushing on each other, colliding, or exploding, or something like that, the force is internal to the system. It does not contribute to the external impulse. That's the beauty of including that. Sometimes in problems, as we've seen, the problem itself will state the system, and you must follow that convention if you're going to analyze it. We got to draw a free body diagram of the objects. We exclude any internal forces to the system. We have to determine if there's an impulse acting on it. In a collision, if the time is very short, we assume the impulse of a non-contact force is about 0. So for example, in a collision, we assume gravity acts a very short amount of time. We assume friction. We assume ropes. Those kinds of non-normal forces, we assume that they collide for such a short amount of time that they don't exert an impulse on it. Remember, impulse is a vector. We set up an expression or calculate the impulse. We set up an expression for the initial momentum, the final momentum, and then we apply impulse as the change in momentum. And remember, if the impulse is 0, then that means the final and the initial momentum are going to be equal to each other. So let's go through a few problems here. So here we have a graph problem. So let's start with just look at the graph. We have a position versus time. So the y value here is going to be our position. The slope is going to be the change in the y variable over the change in the x variable. And that you should recognize as the average velocity or just velocity. The area would be the y variable times the change in the x variable. And that has no meaning. Okay. So 2 blocks move on a straight level track with friction between the blocks and the track is negligible. Okay, block B of mass 4 kilograms initially at rest. So block B is here. It is 4 kilograms. Block A, mass 2 kilograms, slides to the right and collides with block B at time t equal 3 seconds, right here. Which of the following is most nearly the momentum of block B after the collision? Momentum of block B after the collision is the m times v. Now, what do we care about? We care about the slopes being the velocity. So this is the graph of block A as a function of time. So we need if we think about the system as a whole, both objects that are colliding, okay, then we say there's no external impulses because the only forces that are acting, if we draw a free body diagram, is mg and the normal force from the ground, mg and the normal force from the ground. And even though they might exert a force on each other when they make contact, that's internal to the system, so we don't draw out our free body diagram. So in the x direction, the impulse is 0. So we would say the initial momentum is the 2 kilogram times the velocity at A plus the 4 kilogram, which is at rest. So times 0. Now, what's the velocity of A? That's why we wrote this down. The slope is going to tell us the velocity here. So you look at this one, it goes over 1 up 2. That slope is 2 meters per second. So that means this is going to be 2 times 2, which is equal to 4 for the initial momentum. What about the final momentum? Well, it's 2 times the velocity of A plus 4 times the velocity of B, and that's going to equal 4. That's going to equal the initial momentum. Well, what is the velocity of A? Well, now the slope is over 1 down 1, so that's -1 slope. So this is 2 times -1 plus 4 times VB is equal to 4. This is actually the whole thing we want, because we don't just want the velocity, we actually want the momentum. So this is -2, add 2, so 4VB is going to be 6, right? And that's what we want. We want the entire momentum. That's going to be D. Okay, pretty straightforward. Let's take a look at this. Block 1 slides across a horizontal surface when friction between block 1 and the surface is negligible. Block 2 then is carefully dropped from a small height above block 1. Block 2 sticks to block 1 and the 2-block system continues to slide horizontally together. Which of the following correctly describes the change in speed of block 1 immediately after block 2 sticks to it? Okay, so let's think about the system as being the 2 blocks here. And let's think about whether or not there are any impulses. Well, we have gravity, we have a normal force, and then this thing has gravity and it exerts a normal force from the block A, but only a normal force, if anything. It sticks together. There's some internal force, but that's internal to the system because the system is going to be both blocks. So in the x direction, we know the impulse is 0. Now, do we know energy is conserved? Because some of these are going to say conservation of mechanical energy. We do not know it's an elastic collision. It did not say it's an elastic collision. So in general, unless they tell you it's an elastic collision, you cannot assume that the energy is conserved. So this one is automatically, the conservation of energy is definitely like wrong answers off the bat. Okay, but we do know in the x direction, there's no impulse. So the overall change in momentum is going to be 0. Now let's look at the x direction. Block 1, if you think about it, like even though he's falling, you might think like, well, he's got some speed, he is falling. However, his velocity is downward. Momentum is a vector quantity. So if we look at the momentum overall, block 1 has momentum going to the left. Block 2 has no momentum going to the left, has no x momentum because he's only falling. So the initial momentum is just the mass of block 1 times the velocity of block 1. Okay, the final momentum is now they're both going to be moving together, m1 plus m2 times the new final velocity. And by conservation of momentum, that's going to be that. So the final velocity is going to be m1 v1 over m1 plus m2, because now after the collision, they stick together, they're stuck together, they have to move together. So this is going to be m1 over m1 plus m2 is a fraction that's smaller than 1. Therefore, the speed has to decrease, has to be less due to conservation of linear momentum. Okay, easy thing to make a mistake to think that, oh, there's some momentum because block 2 is falling, so he's going to add to the momentum. But block 2 has y momentum, vertical momentum. Block 1 has horizontal momentum, and we do not care about the vertical momentum, all right, because momentum is a vector. Now, is the vertical momentum conserved? We don't know that. In fact, it's not conserved because there's all these vertical forces. So in the y direction, F delta t is decidedly not necessarily 0. So the momentum's only conserved in the x direction in this problem, but not in the y direction. Okay, let's look at this problem here. So a block of mass m1 is released from rest at a height h on a frictionless incline. It slides down and collides with the stationary block mass m2 on a horizontal frictionless surface. After the collision, m1 moves back up the incline to a maximum height h max. M2 moves forward with velocity v. Suppose the mass m1, there's some typos in the problem, as m1 is much larger than m2. Estimate how high up the block will move up the incline and justify your answer without only using equations. Okay, so m1's going to come down. It's going to come down. It's going to have some velocity here, right? And it's very, very big. So it's going to have some huge amount of velocity here. And so almost all like that, like there's a huge amount of momentum. And then m2 is going to shoot off to the right, but m2 is very tiny. So there's not very much momentum to the right. So m1 is actually going to continue to the right. Because M2 is ultimately has a very, very small momentum because M1 is much larger than M2. So M1's actually not going to bounce back and go back up the ramp. He's just going to continue to the right because he dominates the momentum, right? Pretty much all the momentum is just M1 times VF, like if M2 is very, very tiny. So the H max is going to be about 0. And the reason you're going to say this in terms of your justification is almost all momentum of the system will be m1 v1 to the right. So after the collision, m1 will continue to the right. Okay? So it actually won't bounce and go back up. So the H max will be 0. Okay, let's derive the maximum height it will go in terms of this one here. Now, when we're sliding down the ramp, we're going to do conservation of energy because the system is going to be the block in the earth. And the block in the earth system, there's no external forces doing work. The only external force is normal force, but it's perpendicular to the displacement. So we do conservation of energy to find the speed before the collision. Now, during the collision, we might lose some energy, which is why we can only go down to before the collision. So we can say m1gh. If you make the reference height h equals 0 here, it only has potential energy because he's released from rest, right? So the velocity is 0, so there's no kinetic energy in this guy. And then down here, we just have VF squared. We just have kinetic energy. That cancels there. You get the VF is square root of 2GH. Okay, then we're going to do conservation of momentum. The initial momentum, if we say right is the positive direction, is m1 vf, and m2 sitting at rest here, so it's just m1 square root of 2gh. And the final momentum is m1 is, well, let's just, because right is positive, we'll get this velocity here will be up the left, it'll be negative. It'll be m1 v1 plus m2v, and that's equal to m1 square root of 2gh by conservation of momentum. Why is there no momentum? Because if you think of the system as being both blocks, there are no horizontal forces. This is the x direction momentum here, right? Horizontally, because the only forces external to the system are going to be gravity and normal force, and those are in the vertical direction, right? So then we're going to get this kind of equation here. And then we can then do conservation of energy from this guy to go back up to here. So we can solve for V1. Well, V1 will be m1 square root of 2gh minus m2v divided by m1. And then we'll do similar conservation of energy. We're going to get m1 gh max is going to equal 1/2 m1 v1 squared. The m1's cancel. H max is equal to v1 squared. There's a 1/2, and we're going to divide by g over 2g. So it's going to be this thing squared divided by 2g here. So that's going to be our very, very messy equation for that. But that, in principle, is what you're going to do. Suppose the collision was an elastic collision instead. Assume m2 is still moving at speed. So now we're changing the scenario. This is part of the QQT questions. Is assuming block m2 is still moving at speed v after the collision, it was elastic. Predict how it will affect the h max and it reaches m1 reaches. Well, now we're not going to lose any energy. So m1 will have more energy because no energy is lost to the collision, so it will move higher. Reach higher h max. Okay, so we won't lose any energy to the collision. Everything will go back into V1, M1, and then we'll come back up. All right. Let's look at another one. Person of mass m1 is standing on a stationary skateboard of mass m2 on a frictionless surface. The person jumps off the skateboard with an initial velocity v0 at angle theta above the horizontal relative to the ground, causing the skateboard. So the skateboard's going to go this way while he's going to the right. Suppose the person jumps at a larger angle theta while still jumping with the same speed v0. Will the final horizontal velocity of the skateboard be greater than, less than, or the same as before? So what's going to happen is overall the initial momentum in the x direction is 0. And if you think about the system being the person in the skateboard, there's only gravity and normal force. In the x direction, we do know the impulse is 0 because there are no horizontal forces. Y direction, maybe, maybe not. Probably hard to tell because the acceleration is going to vary. The skateboard's not going to have a vertical acceleration, but this guy's going to accelerate upwards. So that means the normal force is actually going to be larger, okay, than the gravity during the interaction. So, but suffice to say, horizontally, we know that the impulse is going to be 0. Now, if he changes the angle but keeps the same velocity, what's going to happen is the overall velocity of the person to the right is going to be less. So the momentum to the right is going to be the less. And if the overall momentum is 0, then that means the skateboard, the whole reason the skateboard moves to the left is the total horizontal momentum has to remain 0. So as the person moves to the right at all, then the skateboard moves to the left. That's why if he jumps straight up and down, the skateboard's not going to move left or right. Okay, so it's going to be less, and that's because at a larger angle, the horizontal component of momentum of the person decreases. So the momentum, because the total momentum of the person plus the skateboard should remain 0 by conservation of momentum. Momentum, thus the skateboard will move slower. Has less momentum to the left. Okay, so that's it. That's all you want to say there. So let's derive an equation for the horizontal velocity of the skateboard. So the initial momentum is 0. The final momentum is going to be the person, he's mass m1. If we say right is the positive direction, he's going to move to the right with v cosine, like the x component of his velocity is going to be that v. You're going to make the right triangle. This is v0 cosine theta. This is v0 sine theta. Again, because momentum's a vector, we're only looking at the x direction. That's going to be m1 v0 cosine theta minus the mass of the skateboard times his velocity. Overall momentum should be 0. It's a minus because the skateboard is going to be moving to the left. And so the v, move that over and divide by m2 is m1 v0 cosine theta divided by m2. Right? Okay, so does your equation agree with our reasoning? Justify why or why not? So when theta is less than 90 degrees and theta increases, then cosine theta goes down. Right? Because cosine is maximum at 0 degrees, right? So cosine theta decreases, thus v will be less. So it is yes. It does agree because we said that it increases the angle. We expect the speed to be less, like that.